Hi everyone, welcome to the second episode of Circuit Series. In this episode, we are going to see PWM generation using IC555 and how to drive a DC motor using it. We will be discussing about the working of this circuit in detail and what is the significance of each of these components. Be sure to check out our circuits library, which has about 200 plus circuits, each categorized for easier browsing. I have left the link in the description to check it out. Let's not waste any time and let's get into the video. For the purpose of explanation, I have split the video into three parts. First one, Astable multivibrator using IC555. Second one, PWM generation using IC555. And the third one is motor driver using transistor. I have left the respective timestamps of these parts in the video description so you can check the parts which you are most interested in. The Astable multivibrator's main function is to generate square wave pulse of particular frequency. To understand Astable multivibrator, we first have to understand the internal diagram of IC555 and how it switches its output high to low. So to set up a Astable multivibrator using IC555, we have to connect a resistor from VCC to pin 7 and another resistor from pin 7 to pin 6 and another pin 6 and pin 2 connects together and a capacitor goes from pin 2 to ground. So this is the common setup of Astable multivibrator that we might have seen across internet as well as in our textbooks. So this is how it works. So this is a capacitor, and if you observe pin 6 and pin 2, these two are internally wired to a comparator. So the function of comparator is to compare incoming voltages. Here, as you can see, pin 6 and pin 2 feed one input of the comparator, whereas the other input is connected to this resistor voltage divider network. So if you can see this, the reference voltage here at this point will be 2 by 3 VCC because there are three resistors and it is all being equal values. So the reference voltage here will be 2 by 3 VCC or VDD in this case. Whereas the trigger reference voltage will be of 1 by 3 VCC. So the trigger voltage and the threshold voltage will be compared against these voltages, and comparator activates the R and S pin of RS flip-flop accordingly. Right? So a capacitor is connected to pin 2 and pin 6. So in an essence, we can say that this capacitor voltage will decide the state of this input pin, these input pins in these comparators, right? So let's say that the circuit is being powered on. When a circuit is powered on, capacitor voltage will be generally at 0. So at this point, this voltage at this pin will be 0 and this pin will be 0. So here 1 by 3 VCC, the reference voltage here will be 1 by 3 VCC, and therefore it will be greater than this capacitor voltage. So it means the set pin will be at high active state, which means high. So here the capacitor voltage is 0 and therefore the threshold voltage is 0. So it means the negative will overpower and the reset will be fed as 0. So this forced the state Q equal to 1 and Q dash equal to 0. So as you can see, this Q dash is connected to a base of a transistor. This is a discharge transistor. I will come back to this later. So here it is the Q dash equal to 0, which means there is an invert operation here and the output will therefore be high. So let's draw here. So the output will be high here and it is indicated as 1. The capacitor will continue to charge through R1 and R2. So at some point the voltage at the capacitor will exceed this trigger voltage. When it exceeds the trigger voltage, the set pin will go to 0 since it is a non-inverting input and it is an inverting input, and it will force the output to 0, whereas the capacitor voltage will still remain under threshold voltage. Therefore, this reset pin of RS flip-flop will remain unchanged. If you look up to the truth table, at this point the RS flip-flop will retain its previous state and will not undergo any change. So this means our output of IC555 will remain at the high state and will continue to exhibit 1 in its output, and the discharge transistor will still be in off state. So the capacitor will continue to charge, and at some point it will cross the threshold voltage, which is a reference of 2/3 VCC. At this point, the reset pin of RS flip-flop will be fed with high state, which is 1. So it means now the state of this RS flip-flop changes. So at this point the reset will be 1 and our set will be in 0 state. If you look up to the truth table, you can see at this point Q equal to 0 and Q dash equal to 1. So when Q dash equal to 1, this inverts the state of this Q dash, and therefore our output of IC555 will go to low and it exhibits 0 state. So now the interesting thing is, so far the discharge transistor was just off, but now because this state has just been active and the discharge transistor was turned on. So if you observe the path of our capacitor current, so R1, from R1 it goes to R2 and it goes to the capacitor, but it was connected to discharge pin and it was off, so therefore there was no discharge of this capacitor. But now, since this discharge path has been open, the capacitor will start discharging through R2 and the current goes to this way and it discharges. So here if you observe, R1 will not take part in discharge, it takes part only in charging of the capacitor. So it is an important thing to remember. So when capacitor starts discharging, it drops, the voltage across the capacitor drops. So now it is little higher than our threshold voltage. When the capacitor voltage drops, it will fall less than this threshold voltage, which means now R will go back to 0 state. 0, let me just draw a 0 right here. So R will go back to 0 state and S will remain in 0 state. Okay, so if you look up to the truth table, there will be no change in the output and it stays the same. So the output of IC555 is going to be low for this condition as well. So now the capacitor will continue to discharge, and at some point the voltage across capacitor is going to fall below this trigger voltage. When it drops below trigger voltage, now the set pin will be the trigger voltage. This reference voltage here 1/3 VCC will be more than the capacitor voltage. Therefore the set pin will be 1 and the reset pin will be 0. Now if you again look up to the truth table, you can observe that Q equal to 1 and Q dash equal to 0. Now it is being 0, this discharge transistor will turn off. Therefore the discharging of this capacitor stops, and now the output will switch back to high state, since it will invert what is being the state being in the Q dash pin. So now as you can see, it forms a cycle, high, low and high. So this charging and discharging process continues, thus generating a high and low pulse of square waves of particular fixed frequency. The important thing to note here is the charging path and discharging path. In the charging path, the charging current goes from VCC to R1 and then it goes to R2 and then it reaches C2. So it means that it involves two resistors for charging this capacitor. Whereas in discharging, the discharging current from capacitor will go from C2 then to R2 and then to our discharge transistor where the current flows via this transistor. So it means our R1 will not take part in discharging. So this implies the charging process will take more time than discharging. So in a essence, if you remember that while charging this capacitor, our output of IC555 will be high. So it means the duration of charging, that is duration of high pulse, high state, will be greater than discharging, that is greater than duration of low pulse. So this is for charging, this is for discharging. So in a way we can say IC555 as an astable multivibrator will never, the duty cycle of IC555 astable multivibrator will never go less than 50% or 55% for that matter. Even when you choose this resistor R1 very less compared to R2, there is still always our duty cycle that will exceed 50%. That is, the charging duration will always be greater than discharge duration, that is low time. So now we need to modify this property of astable multivibrator to be able to successfully generate PWM pulse, and that is what we intend to do. We will make little modification to this astable multivibrator setup, and therefore we will be able to successfully reduce this high time. Maybe we can reduce up to 10% or 20% or whatever it may be in order to successfully generate PWM pulse. So this goes the same, this goes other way as well. So we can exceed this duty cycle to 80%, 70%, and the only common thing that you need to remember is astable as IC555 as an astable multivibrator, its duty cycle cannot go less than 55%. So we need to modify this in order to generate a PWM pulse. Before heading into the next part, allow me to introduce you guys to PCBWay, one of the best PCB manufacturers in the world. Their quick turnaround time, vast delivery network, cost-effective services makes them a best option to get your PCBs manufactured. Not only they will manufacture FR4 and aluminum PCB boards, they are specialized in manufacturing advanced PCBs like Rogers, HDI, Flex and Rigid Flex PCB boards. So visit www.pcbway.com now to get your PCBs manufactured. I have left the link in the description so you can check them out. PWM generator using IC555. This is the PWM generator circuit which we have built using IC555. If you notice, this is pretty much the same astable multivibrator with few modifications. You can observe there is a resistor going from VCC to pin 7 and a capacitor connected to pin 2. Here the major modification we have made is we have replaced the resistor R2 with a potentiometer or a variable resistor RV2 and a couple of diodes D1 and D2. So if you remember the operation of astable multivibrator, it solely depends on charging the capacitor and discharging the capacitor. Here, if you turn the circuit on, the capacitor will start charging and the charging current from VCC will go through R1, whereas in our previous circuit it will go through R2 and it will reach C2, whereas here we have given two different paths. So let's assume the circuit is powered on. The charging current from 5 volt will go through R1, and here there will be two different paths for it, and as you can see, D2 is forward biased and D1 is reverse biased. So this D1 is going to block the charging current and this D2 is going to allow it. So the charging current will take this path. It will go from VCC R1 and then through D2 and then it reaches to C2, right? So if you know about variable resistor, it has 3 different terminals, and when you modify the pot, that is the center cylindrical thing in a variable resistor, if you modify it, you can observe there will be a different resistance exhibited. For example, if you modify the resistance value using the pot, you can observe different resistance between 1 and 2 and 2 and 3. That is what we are trying to achieve here. So if you let's say you have modified this resistance value, which means this charging current will experience different resistance here than the discharging current. So now the capacitor is charged and it has given a high pulse in the output. Let's say that, and once it finishes charging, and when it moves on to discharging, here the discharging current from here goes through R2, and here now D1 is forward biased and D2 is reverse biased. So D2 will block the discharge current and the reverse discharging current will take this route. It will go through D1 and it will discharge through discharging transistor connected internally to it. So now you can understand that there is two different paths provided in this circuit. So as I said, this pot has different resistance across 1 and 2 and 2 and 3. So let's consider a scenario to understand this better. Let's say that you have modified the resistance value, so the resistance between 1 and 2 is actually 1, 2 terminal exhibits resistance of about 10k. So this is a 100k pot, and here we have set the pot in such a manner 1 and 2, the resistance between 1 and 2 exhibits about 10k of resistance, which means 2 and 3 will have about 90k of resistance, since it is being a 100k resistance, variable resistance. So it is being split into two. So here when you set it 10k, and it will be exhibiting 90k of resistance. So now if you see the charging path, the charging current will go from R1 then to D2, then to terminal 1, and then flow into the capacitor through terminal 2. So it means when you sum up the resistance of R1 and 1 and 2 terminal here, the total resistance exhibited here, exhibited for charging current, will be around 12.2k. So now if you consider the discharging path, here it is 90k, which is more than or 12.2k. So through this manner we can say that the charging of the capacitor will take less time comparing to discharging of the capacitor. So this implies that our charging time will actually be less comparing to our discharge time, which means, remember from the previous section, when the capacitor is charging, our output will be high, and when the capacitor is discharging, our output will be low. So this means our reduced resistance in the charging path will give a short duration of high pulse, and the higher resistance in the discharge path will give a higher duration of low pulse. So it implies that we can successfully modify the duty cycle of below 55%, which is the default criteria for Astable multivibrator using IC555. So it goes both ways. So if you increase the resistance in the discharge path, it will yield a high duty cycle. If you increase the resistance in if you increase the resistance in charging path, it will yield you a high duty cycle somewhere around 80 to 90, even to 100% of the duty cycle, not exactly 100. close to 95, 97, somewhere around that. When you increase the resistance in discharging path by setting the potentiometer in that manner, so you will yield a duty cycle very less, which is around 5% or 10% or something like that. So you will be able to successfully generate a PWM pulse, which can be of modified width, and that is what is all about PWM pulse. Right, so I hope you understand this. Using this modification, you can change the duty cycle anywhere between 5% to 95% successfully, and that modifies the basic behavior of astable multivibrator using IC555. Now we have come to the final section of our video, transistor driver. So IC555 has generated a PWM pulse now. So now we have to drive our DC motor using this PWM pulse. IC555 can only source about 200 milliamps of current, which is not really sufficient. I have measured my current of DC motor under 5 volt, which is about 500 milliamps, and there is no way IC555 can handle that current. So I have used a transistor CL100 to act as a switch, and when there is a PWM pulse, when there is a high in the output, this transistor goes into saturation region. The high pulse here will push the transistor to saturation region, and therefore it closes the circuit and the current flows through the DC motor and from collector to emitter, thus closing the circuit, and therefore the DC motor will run. So that's how a transistor is being used as a motor driver here, and it is not really possible to drive DC motor using IC555. Even though the datasheet states it can handle up to 200 milliamps, but it can get extremely hot, and it is very unlikely in practical application for IC555 to handle such current. So therefore it is always suggested to use a transistor as a switch and connect it in this way. You can either use a PNP or NPN. This is a NPN transistor. You can use a PNP transistor as well to act as a motor driver here. So also remember, you need to use a diode here. This is a flywheel diode, where when an inductive device is turned off, it always tends to send a reverse negative voltage spike, and this diode will arrest the voltage spike, and it will prevent the rest of the circuit from damaging due to the voltage spike. Let's get into the quick summary of this circuit. This circuit uses a modified astable multivibrator using IC555. When capacitor charges, output of IC555 will go high, and it goes low when capacitor discharges. To generate PWM pulse using this modified astable multivibrator circuit, charging and discharging path of capacitor should be different and should possess different resistance. 555 timer IC cannot handle high current to drive a motor by itself. So in order to do that, we are using a transistor as a switch in order to drive the motor, and it serves as a motor driver. Check out the related article in our website, where we have explained this circuit with mathematical calculations. I have left the link in the description below, so you can check them out. Hope this video was informative to you. We are looking for your honest feedback. If you have any kind of feedback regarding the explanation of circuits or our presentation, or if you like us to cover any particular circuit in this series, please leave a comment in the comment section below. It will be helpful for us to improve the quality of this series, and we will be able to cover as many circuits as possible in this series. Give this video a thumbs up if it was useful to you. If not, leave a thumbs down. Subscribe to our channel if you want to see more of these videos, and hit the bell icon if you like to be notified about it. Thanks for watching. See you next time.